What causes local buckling to limit structural capacity? Imagine a tall, slender tower or a thin metal beam. You might think it can hold a lot, but sometimes it fails sooner than expected. That's often because of a process called local buckling. When parts of a structure buckle or deform under pressure, it can stop the whole thing from holding weight. This is what limits how strong a structure can be. Local buckling happens when a small part of a cross-section, like a thin plate or wall, bends or crumples before the entire piece reaches its maximum load. Think of a soda can. If you press it gently, the sides might bend or buckle first, even if the can isn't crushed completely. This kind of failure is common in thin-walled sections, like steel beams or columns. One big reason for local buckling is the shape of the cross-section. If the plates or walls are very slender, meaning they are wide but very thin, they are more likely to buckle early. High width-to-thickness ratios make these plates less resistant to bending or wrinkling under pressure. So, a thin wall that is very wide compared to its thickness is more prone to buckling before the entire structure fails. Another cause is how the load is applied. When a compressive force pushes on a member, the stress isn't spread evenly. Some parts, especially thin plates, might experience higher stress concentrations. These areas can deform or buckle locally even if the overall load is still below the material's breaking point. Support also plays a role. If the edges of a thin plate aren't supported properly, it can easily buckle out of its plane. Without lateral support or stiffeners, the plate can deform sideways or outwards, causing local failure. That's why engineers add stiffeners or braces to prevent this kind of buckling. Design choices matter too. Engineers often make sections with very thin walls to save weight or increase efficiency. But these thin-walled sections are more vulnerable to local buckling. They can buckle independently of the entire structure, limiting how much load they can carry. Material properties are important as well. Materials with lower stiffness or elastic modulus tend to buckle more easily. If the plates have a high width-to-thickness ratio or are made from less stiff materials, they will reach their buckling point sooner. The type and distribution of load also influence buckling. Concentrated loads, like a heavy weight placed on one spot, can cause local buckling faster than evenly distributed loads. How the load is applied affects which part of the cross-section fails first. Once a part of the cross-section buckles, it can no longer carry as much load. This reduces the overall strength of the member. For example, if the web of a column buckles, it might cause the entire column to become unstable. This failure often happens before the entire member reaches its maximum load capacity. In structural design, engineers categorize cross-sections as compact, non-compact, or slender based on their width-to-thickness ratios. Slender sections are more likely to buckle locally and need to be designed with lower allowable stresses. Knowing what causes local buckling helps prevent unexpected failures. By designing with thicker plates, adding supports, or choosing stiffer materials, engineers can keep structures stable under compression. This understanding helps ensure safety and make sure that structures last longer without failing prematurely.